with Shinji, and then I don't see anyone from attendees. So okay, Shinji, go ahead.
Yes, so I want to ask the same question to Enrico about this formation of this universal horizon. So you explained that it takes infinite time to form the universal horizon. Is that right?
Yes.
I see. Yeah.
Yeah. So asymptotically, you see the. I mean, it's when you do simulations of collapse in GR in the maximum slicing gauge, that's equivalent to a simulation of the collapsing Hojava gravity, at least in a certain version of Hojava gravity, and the surfaces of with k equals 0, they're surfaces of constant Cronon. So and you see, there are classical papers in the 80s and 90s where they do this, and they see really the hypersurfaces of k equals 0 piling up at r equals 3/2 m, which is the location of the universal horizon in the limit. They pile up at the location of the universal horizon. And I think this checks out because, in fact, you do expect the universal horizon to be a Cauchy horizon, so you shouldn't be able to evolve past that.
I see. So in that case, say if we consider spherical symmetry, then the center of the symmetry is always covered by constant time surface.
The center of symmetry is outside the domain you simulate, essentially.
But if we start from regular initial data, then r equals 0 is included. And then we evolve, r equals 0 is included, and at some point it disappears, or it is, I think it is always covered.
No, no, because you never form, what I was trying to say is that you never form the universal horizon. R equals 0.
That's what I mean.
Yeah, no, r equals 0 is always, you're right, it's always inside. And but you never actually form the universal horizon at finite times.
I see. So do we still have even in that case, do we have any observational effects from this asymptotic behavior when we are far away from?
I don't think you have low energy observables because you still have effective low energy horizons for the spin 0 and the tensor modes. So those, they act as low energy horizons, and they reprocess. I mean, the radiation that can, or the modes that can escape from near the universal horizon, they must be very high energy.
Right.
And they are, in any case, they are reprocessed by the low energy horizons which are outside. So I don't think we have any observation. Of course, if the answer is I don't know, but I don't think we do have any. Or I toyed with the idea that maybe this universal horizon becomes unstable away from spherical symmetry, and then you could form a hard surface. And then it could be an ultra-compact object like of the kind that the people in ECHO. But still, anything that escapes from there, I mean, if it is low energy photons or low energy excitations, it's trapped by, it's reprocessed by it's trapped by the effective horizons which are outside. So you would need very high energy excitations, I think. I don't know if this.
Can I make a comment on this?
Go ahead.
Yes, please.
I think that it's a very important point that basically there is a topology change in the constant Cronon surfaces. And in fact, you will never be able to see it as a continuous process, exactly because of what you were saying, Shinji. But the effect, it can be dramatic at the quantum level, at least, because it implies that the vacuum that you set up after the snap of the surfaces is going to be a vacuum where you have a very strong UV dominance, in a certain sense, which is very different from the standard adiabatic evolution that you have from Minkowski vacuum to the Uru vacuum when you onset an horizon. And this non-adiabatic process, I think, is crucial in understanding the thermodynamics associated to this universal horizon, which seems to be required for consistency of other aspects that are emerging, in the sense that if you want to have a consistent thermodynamic for these objects, the universal horizon appears to be the crucial ingredient.
I see. I see.
So can I comment on this? I see Raul, but I just this point of topology change, because this keeps coming up, and I kind of don't see the argument for that. What is,
because the constant Cronon surface, they snap from closing to I naught to closing on I plus. Basically, what is happening is that before is a kind of open surface, and then once you close on I plus, it means that it's really becoming a compact object, because you can stay all inside this kind of sphere, you can imagine, right? So from that point of view, this changing from I closing to I naught to closing to I plus is basically what I think we are referring here as a topology change.
I mean, I'm kind of, I guess you are speculating about might be happening due to quantum effect, but I mean, classically, all that happens is just evolution freezes as you're approaching this universal
Of course,
horizon.
but because your convolution is continuous, you will never be able to see a topology change of these surfaces.
But why
you will
should
never
there be a topology? I mean,
because you're not closing on I naught, you're closing on I plus. It's dramatically different what is happening now, right?
But again, I think you're
it's a constant radius surface becoming.
It's a time-like surface, so it's saying something about. I mean, the reason I'm saying is that it's kind of, we've done simulations of this numerically and analytically, and I don't really see this idea about.
Sorry, but yes, I think you find the same result, because I mean, in a different context, we find your same result. I think what they're saying is that you can only form it in an infinite time, which is what you find in your.
But so the question is this topology change that why do you think there must be a topology?
Because when you look at the statics configuration, you'll see that that's a different topology. The problem is that you cannot follow this continuously, or you can just see it approaching an infinite time, exactly because it is this change. You cannot see the surface snapping from I naught to I plus. That it will never happen to you. You have an infinite accumulation of constant Cronon surface close to that, and this is what you see.
That's right, and I'm saying that's the whole story. I mean, that
is proving that at the end there is this accumulation surfaces which has this new property of closing on I plus. But you realize that is completely different. It means that any object that reach I plus can influence the whole universal horizon.
That's right.
I mean, it's a radically different situation now. Anything that reach I plus is causally connected with the universal horizon. Any point of the universal horizon.
No, it is very radical. I agree. So Raul, you wanted to say something?
Yes.
On the same topic, or is it a different topic?
No, it's the same topic. That's why I wanted to.
Go ahead, Raul.
Just before we switch. So something that is related to this issue of topology change and the definition of the universal horizon. So it's something that I've been working with Stefano, Francesco, and Matt here. So if perhaps they also want to comment something, but it's that the fact that with the universal horizons you see this topology change or you see this peculiarity is also associated to the fact that you are using a definition that is valid in static situations. So you are just looking at static situations, but so it's kind of the same to what happens with the event horizons versus trapping horizons, right? So you can also do the same, play the same game, and essentially try to define a quasi-local version of universal horizons. And then let's say that the one that we are discussing, in which you have this topology change, is the global one, like the similar, the equivalent to the event horizon in general relativity. But the quasi-local version doesn't need to have this topology change. So in principle, there are no issues with forming this in gravitational collapse. So yeah, essentially, it's like there is as in general relativity, there is the global version and the quasi-local version. So you can also do the same with universal horizons, and this may play a role in the question that Shinji asked.
I see. Thank you.
Oh, thanks, Raul. So Luciano.
Yeah, so well, first of all, thank you. Well, I think this is exactly the point I wanted to make on this topic. That is, thinking about event horizon can be very misleading, especially if you're trying to model a dynamical spacetime. In that case, you better resort to something which is maybe not as global, but at least makes sense and doesn't create this discussion, is there a topology change or not? But my question was really to Carlos, and so I will start with a remark. I think the concept of exoticity is it's like the concept of beauty. It changes with time. Whatever we find exotic today may be just perfectly normal in 20 years' time. And don't forget that black holes were considered exotic, and some astronomers still think they are exotic. Nevertheless, we have to keep in mind that there are astronomical observations, and we know there is matter in the universe, and this matter will be accreting on whatever compact object we can build. So, I'm happy with you creating any static ultra compact object, but over time, especially if you produce them cosmologically, these guys will have accreted huge amounts of matter. So can you imagine that your accretion process would be always such that it will just be a minor perturbation to a static configuration, and then you will never actually trigger a collapse to something that will at the end be a black hole with all the the consequences that this brings in?
The way in which I imagine these things is that it is very important to separate between the presence of trapped surfaces and horizons, which I call, long-lived horizons. I'm pretty sure, I think that all the arguments are such that it is not really possible to avoid the formation of trapped surfaces. As you are saying, I think if I have one of these ultra compact objects that initially is completely empty of matter, is very idealized, and then I throw into it some accretion, then I'm almost sure that these objects would generate some trapped surfaces. So in intermediate stages, they will have some characteristics close to black holes. But the problem is that how much time from an external observer these objects, how much time it takes for this object to adapt to a new situation. And that's the real, I would say that there are like different regimes. If you throw matter continuously to one of these objects, then you can make this to be very close to a black hole for as long as you are able to throw matter into it. But if this matter, for example, is falling down in bursts, in lumps, then it's a matter of controlling which is the time scale of the adaptation of these objects to new configurations in which they try to go outside the horizons. What we are suggesting is that the horizons they can only exist if they exist for short periods of time, and then you have this object, you collapse it, but then it tends to go back to a configuration which is outside the new horizon. And
sorry, what makes the bounds? I mean, what is at the origin of this expansion again?
So I couldn't elaborate on that in the talk, but the thing is that here there is other, they might be, the semi-classical physics in dynamical situations might have some clues about that, but it's more difficult to analyze, and we cannot say more right now. But there are other ideas, as the one that I was suggesting with these emerging gravity theories, in which what happens is that the bounds are produced because gravity, when it reaches very high energies, when matter collapses and goes to Planckian densities, then it's sort of disconnected. It's like if you find a regime in which the theory is free, and then there is no longer gravity, and then matter is just bouncing back from the internal regions to the external regions. And then and this is a way to connect solutions that are similar to black holes, to collapsing black holes, to solutions that are also classical, but there are white holes. And what we are speculating is that matter, in combination with this well, strange, if you want, way of behaving of the geometry, is able to oscillate between configurations that are black hole-like and configurations that are white hole-like until they reach a new equilibrium, which is the one that I have been analyzing. The equilibrium, the final results, not the transients, which are, as I said, much more difficult to analyze.
Okay, thank you.
This is the idea that we have. Yeah.
Okay. Thanks, Carlos and Luciano. I saw Paolo has raised his hand. Paolo, what do you want to talk about?
Yes, so I just wanted to follow up on Luciano's second question, so about accretion, which I think I agree is a very important point. I think that an important ingredient is the reflectivity, essentially how much energy does the object absorb or not. For example, there was this argument many years ago by Broderick and Narayan, showing essentially that if, say, a gravastar or anyway an exotic compact object with a hard surface is in thermodynamical equilibrium, eventually should shine radiation, and that puts a very strong constraint. I mean, not seeing that radiation, say, from Sagittarius A, puts very strong constraints on the model. At the same time, there is a paper, I think by Francesco Di Filippo, Stefan, and others, Carlos maybe as well, showing that the moment there is even a tiny reflectivity, meaning a small absorption from the object, that bound is almost relaxed completely and can be evaded. The same thing might happen, say, for boson stars. If one does not couple at all, say, the scalar field with matter, so it really considers it as an independent field, then I agree. I mean, Luciano also has paper on this, that matter will start accumulating at the center. It might shine or eventually even collapse to a black hole. It's less clear, I think, what will happen if the object starts interacting a little bit with matter. At which level do these constraints, can these constraints be evaded?
Mm-hmm.
I agree with you. Yeah.
So I think it's a very good point. And I think one thing I wanted to mention is this obvious, there is this notion of, there's a little bit of a disconnect that I've noticed talking between, relativists and, people who work in a string theory and quantum gravity that, of course, relativists think that everything is going to form a black hole. That's kind of our training. But then people who work on quantum mechanics then think about basically things getting out and tunneling out. And I think there is that is the connection that's missing. And it's a connection that at some point someone needs to make, a bridge that needs to be built. That, it's not classical relativistic ideas that are going to build this. There will be some quantum idea, and in particular, these quantum ideas will be tunneling out of the classical black hole solutions. So, that's I do wonder whether eventually we need some sort of quantum simulations, or maybe even holographic quantum simulations of holographic duals to these black holes, because that might be really what's needed to answer this question fully, because really it's the quantum effect that we're talking about, and not the classical, and not possibly even a semi-classical one, even though Carlos has been advocating for a semi-classical picture. So I did see Shinjiro raise his hand again. Go ahead, Shinji.
Yes, I have a question to Carlos. So the first, before asking question, I want to make sure that I understand your solution. So you consider the quantum field, and the computer team union, and so that I guess your non-trivial solution is due to the negative energy of this Borel state. Is that right?
Yes.
Okay.
Yes.
Yeah. So in that case, if you consider many quantum fields, then you have large negative energy. And if you have, say, bosonic fields and fermionic fields, and depending on the combination of numbers, you have definite number. And so if you consider, say, standard model particle physics, then do you still get non-trivial solutions for realistic size of the astrophysical object?
I mean, it's an interesting question, but I cannot answer. I haven't done. We haven't done an analysis beyond the very simplest. Well, we have done this with a massless scalar field, and it would be necessary to analyze this in different fields, and then to add all of them, and to see whether the picture is still there or it's modified in some sense. I mean, I cannot.
Yeah. So then let me ask in this way. So that do you need a lot of many fields, or just a few fields are okay?
Well, the thing is that there is this. For me, I think it's interesting just to analyze what happened with one field, in the sense that it's sort of instead of thinking that this is coming from semi-classical ideas, you can say that this is a modified gravity, which has a specific form, which has these non-localities plus some high curvature. So, and then you analyze this thing. Another issue is when you put this into a scheme which is more quantum gravity-like, and you want to analyze how much consistent is this semi-classical approach. And then when you do that, the typical reasoning is that you have to have many fields, many matter fields, in order that you can sort of forget the quantum fluctuations of the gravitational field itself. And but I don't think that, well, in this way of trying to understand things, I don't think it's really so much necessary. I mean, I try to think about that more into the idea that you have some heuristic ideas leading to a modified gravity theory.
I see. Yeah, but anyway, one field is enough to support your solution. I think that's very nice. I thought before I mean asking this question to you, I thought that you need a lot of fields, but no. Just one field that's very nice. Yeah, thank you.
Okay, thanks, Shinji. Stefano?
Yeah, I had a question for Carlos, but I was very interested in the proposal by Shinji, because I think, Shinji, are you thinking that if you have something like supergravity, you can switch off this vacuum polarization?
Maybe yes. Yeah.
This is what you.
But
fortunately, if any, sorry, supergravity, supersymmetry. If any supersymmetry, yes, then it should be broken for these astrophysical objects. But maybe. I think that the key point for if you want to get rid of horizon, you need to find effects that are aware of the horizon. And in order to be affected by the horizon, some people say, well, the equivalent principle forbids it. But you may have objects which are not ultra-local; they are quasi-local. This is something that, for example, Matt here has insisted very many times in trying to explain. And one thing that is not ultra-local is the two-point green function. When you have an Hadamard structure, you really need to. You are able to probe the tidal effects, basically, which is really where gravity is encoded. Divergences like the Candilas one in the Bulbar vacuum are the key point. So as long as you have, even that the balance of the 0-point modes as a total energy is small, but as a structure which is able to feel the closeness to the formation of an horizon, like the Candilas divergence in Bulbar vacuum, then you may have a mechanism that is trying to avoid that divergence, right? So the problem is that how you can dynamically make this effect important, that is another matter, because in a free fall collapse, it will never be able to stop and to onset this vacuum polarization will always be negligible. So I think that the key point in forming is more the dynamics. I'm not so surprised that you can find the static path, although it's very interesting already to be able to build it. And there is my question for Carlos, which is your wormhole structure. I have two questions. One is, have you tried to consider, because you would say I can refine possibly the regularization of the regular behavior of the Polyakov stress energy tensor close to r equals 0, and maybe that avoids the singularity behind the throat. But can't already be an amelioration if you put the things in rotation? Astrophysical object will rotate. If you rotate, you replace, you don't have this focusing point. You will have, you have to regularize the ring, if you like. So my first question is, are you sure that rotation is not another ingredient that is crucial in making this structure more realistic. And the second point is, can your throat be a null throat? So that from outside is a wormhole throat, but nonetheless is a null surface. So it's very difficult to distinguish from this point of view from an horizon until you are there and you realize that that is a throat. It's not an horizon, which technically is different because the expansion of the ingoing outgoing congruence will be differently there. So these are my two questions for you guys.
Well, regarding the last one, the null throat, it seems that well, at least if you maintain this idea of using this static vacuum, which is this Borwer vacuum, then it seems that it does not allow, it's repel even when you reach this point of this next, precisely the effect of the semiclassical, the main effect of the semiclassical corrections is that this makes the redshift function and the compactness function to go differently. When one goes to 1, the other one doesn't go to 0. And precisely it makes that these next are always space-like. I mean, they are not null. And the null surface is precisely the singular bit. So the singular is in the internal region. And it's also the place in which the pressure typically diverges when you have these surfaces of which are null. So in principle, this Borwer vacuum do not allow that. Yeah. And then the other question.
The rotation.
The rotation, yes. The rotation, well, that's for sure. I mean, in main configurations, for sure, it would be, well, it's the additional very important ingredient that is missing in this analysis. But in fact, I cannot say much about this rotation because even the definition of a Borwer vacuum is complicated. When you start before analyzing self-consistent solutions, you first typically what you do is to analyze the behavior of a field in a curved spacetime with a fixed spacetime. And then if you analyze the behavior of quantum fields in a curved spacetime, what you see is that there is no natural generalization of Borwer vacuum. There are, well, it's because the presence of superradiance in a sense. Mm-hmm. And then you have, and this Borwer vacuum, there are like two types of Borwer vacuum you want. The one based on the past modes and one based on the future modes. And then depending on which precise vacuum do you use, you will have divergences in some regions and in some others. So it's not direct. It's not so easy to extrapolate from the curved spacetime analysis to the self-consistent analysis. I mean, right now, I would say that it's a very interesting problem, but I think there are still. I mean, it's not an easy problem to tackle. Also, the Polyakov approximation doesn't work. So you have to really go for more refined approximations, which have, for the typical approximations, they have higher order derivatives of the metric functions. And then when you analyze the dynamical process, you have to also understand which are the physical conditions in order not to be analyzing spurious solutions. Because many of the solutions that you find in these higher derivative problems are not physical. So, I mean, the problem is complicated a lot.
So, thanks a lot, Carlos. In the interest of time, let's carry on. So, Luciano, do you want to go ahead and unmute? Yeah.
Yeah. So I just wanted to pick up on what Paolo was mentioning, and maybe this is a conjecture and I throw it there and maybe it's just wrong, but I think as soon as you deviate from considering reflectivity equal to 0 and to 1, then you're going to introduce a dependence on the accretion rate. So, and the idea I have is the following. Think about pouring water onto sand, okay? If you pour a little bit of water, the sand will just absorb all of the water. You can pour more water onto the sand and the sand can still absorb the water. At one point, you will be pouring so much water that no matter how porous your sand is, will just start accumulating. And I think this is what is going to happen. So depending on what is the reflectivity that you decide to associate with this surface, you will determine an accretion rate at which matter will start accumulating. At the dynamic, you will produce a shock. And so then it's nature that will decide whether or not you ever reach such accretion rates.
Yeah, that's a very good point. And I think the question is, a lot of phenomenology that has been done is for vacuum. And if you do have matter, really how the matter interacts with basically whatever fuzz that you put, basically the fuzz that makes fuzzball, how matter turns into that. That's certainly a lot of phenomenology that needs to be done. Yeah, for that. That's a very good point. Anyone else wants to comment on that? So it's been half an hour of discussion. It's been a very exciting morning, and I think lots of interesting ideas. I think just one last thing I want to mention is that even though what Enrico talked about seemed a little bit disconnected from the rest of the other black holes, ultimately, if you want to get rid of the horizons, things to go faster than the speed of light. And so I really think those are the same things. Just we haven't found the right connection. But there is one, and so if you want more black hole echoes and gravitational ether, ultimately there will be a place for both of them. But it's for us, it's a homework exercise to find where that connection is. I guess if we run out of topics, and the next session will be in an hour, or maybe in just in 50 minutes. Well, thanks everybody, the speakers and all the participants, and I'll see you guys in less than an hour. Take care, you guys. Bye-bye.
Thanks, Ayesh. Bye-bye.